So what's good, TMG fam? It's your boy Ellen. I'm back with another reaction. How y'all feel? Welcome back to the channel. Salute. Now, let me give a brief warning, because videos like this tend to lead you down a rabbit hole. Trust me. I've been down it. Still down it. You know what I mean? They do, man. Because it doesn't do anything but create more and more and more questions behind it. And that's what it did to me. So I'm still down this rabbit hole. So I'm pulling y'all down here with me. This video here is, was the universe created from nothing? All right. And that's been a question that people have been plaguing people for the longest. You know what I mean? Surrounding the whole Big Bang theory, how the explosion created things and everything started coming from that. But what caused it? My question has been for the longest, what caused the explosion? Was it just total randomness? Was it just like, what? You know what I mean? And we just haven't figured that out yet. It's just like out of nowhere, just boom. And then we're all a product of that, and everything else, and the expansion and all that kind of stuff is a product of that. It's just hard for me to just grasp a hold to that logic and that theory and just not have any questions. So we're going to get into this video, man. If you like this kind of stuff, if you're new, hit that subscribe button, join the fam, and let's learn something.
Modern science explains the origin of the universe with the Big Bang Theory. It says our world arose from the explosion of singularity, or a point in space-time where energy, density, and mass go to infinity, and any dimension goes to zero. It's a point where there's no space, time, or matter. So where did this singularity come from? What preceded it? And what triggered the countdown to the Big Bang? About 1600 years ago, the theologian St. Augustine tried to understand the nature of God before the creation of the universe, and he came to the conclusion that time was part of God's creation and there was simply no before. In the 20th century, Einstein came to similar conclusions with his theory of relativity. With its help, the scientist was able to connect mass and time. Einstein proved that time passes slower for anything close to massive bodies. For example, the gigantic mass of our planet distorts time, causing it to flow more slowly for a person on the surface than for an astronaut in orbit. The difference is too small to be obvious, but it's there. Then, two American scientists, Robert Pound and Glenn Rebka, were able to experimentally prove that a clock on the surface of the Earth runs slower than a clock raised to a height of 22.5 meters. This is exactly the number predicted by the theory of relativity. Of course, in order to become 1 second younger, a person has to spend 1 billion years in a high-rise building. But the larger the mass, the more it slows down time. And the singularity preceding the Big Bang had all the mass in the universe, which completely stopped time. So, according to Einstein, it makes no sense to say what happened before the Big Bang, because this before didn't exist.
And that's the part that gets me. Just think about everything we've come to know about life. There was always a before. You know what I mean? You had a parent before you. That parent had a parent before them, which had a parent before them. So it's like, trying to unlearn that is hard. So when you tell me just nothing and then this just happened, I'm working on it. I'm working on it.
The Big Bang, because this before didn't exist. But this conclusion contradicts one of the fundamental physical concepts, cause and effect relationships.
Thank you.
Any effect must have a cause or a reason. For example, parents are causes that give birth to children.
Same exact example.
Every experience that people have is related to cause and effect relationships. So to us, Einstein's idea that there was nothing prior to the cosmic singularity doesn't feel right. because it implies that the concept of the past cannot be regarded as part of it. So is it possible that St. Augustine and Einstein were wrong? The cosmic singularity could not be the beginning of everything, but generally scientists don't doubt the Big Bang theory. It's the idea supported by facts that were predicted by this theory. It's the expansion of the universe, discovered by the American astronomer Hubble in 1929. It's the relic radiation, or a cosmic microwave background radiation, that evenly fills the entire universe, discovered by American scientists Penzias and Wilson in 1965. The phenomenon appeared in the era of hydrogen recombination, 379,000 years after the Big Bang. According to the Big Bang theory, in the first second of its birth, our universe was no more than an atom, but it managed to survive 6 epochs already. The Planck epoch, that lasted from the beginning of time to 10 to the minus 43 seconds. The Grand Unification epoch, which lasted up to 10 to the minus 35 of a second, during which gravity separated from other types of fundamental interactions. This was followed by the Inflationary epoch, lasting up to 10 to the minus 32 seconds, during which the volume of the universe increased by a factor of 10 to the 78. To imagine how huge this figure is, think of the number of atoms in the observable universe. According to various estimates, it ranges from 10 to the power 79 to 10 to the power 81. Then there was the electroweak epoch, lasting up to 10 to the minus 12 of a second. It's around this time that quarks, leptons, photons, W and Z bosons, and Higgs bosons formed. Then came the quark epoch, during which gravitation, electromagnetism, and the strong and weak interactions took their present forms. And only then would the hadron epoch come, which would end a second after the countdown, and the universe would finally reach the size of an atom. On this scale, the laws of quantum theory take over classical physics. This is why cosmologists, including Stephen Hawking, began to ask the question, what if quantum theory, only used to describe subatomic phenomena, was applied to the entire universe as a whole? And this is when inflationary quantum cosmology was born. The astrophysicist John Gribbin described it as the most significant advance in science since the time of Isaac Newton. It is quantum cosmology that offers a way to get around the problem of singularity and the idea that there was nothing before it. Classical cosmologists believed that the cosmic singularity from which the Big Bang originated was something like a point with zero volume. But according to quantum theory, at the most fundamental level, nature has an inevitable fuzziness, so it's impossible to specify the exact moment of the universe creation, its initial time and volume. Interestingly, the quantum theory allows for the spontaneous emergence of particles from the vacuum. This way of creating something out of nothing made quantum cosmologists wonder if the universe itself, according to the laws of quantum mechanics, arose from a random fluctuation. If so, the reason that there's always something in the instability of the vacuum, or rather emptiness. But don't confuse the void, where there's literally nothing, with the physical vacuum.
But the thing is, though, right? And I keep harking back to that point. You know what I mean? And this is all just fun of conversating back and forth about theories that we may never get the answer to, but it's just fun to converse back and forth about it. My thing is, okay, if nothing was beforehand, something had to cause the explosion. Something had to go on to cause the explosion, theoretically, that the Big Bang or whatever, to cause everything to happen following after that. So what happened then? Something had to be out there, and then something had to explode. Like, explosions don't just randomly, you know what I mean? If we're going to grasp onto that theory and continue to hold on to the Big Bang, which people have shot holes through that theory as well. So it's like, it's hard for me, as y'all can tell.
Don't confuse the void, where there's literally nothing, with the physical vacuum. To a physicist, vacuum describes a state where there are no particles, but overall, vacuum isn't really empty.
Exactly.
One of the principles underlying our quantum understanding of nature is Heisenberg's uncertainty principle.
Heisenberg.
It states that certain pairs of properties are related to each other in such a way that they cannot be accurately measured together. One such pair is a particle's position and momentum. The more precisely you know its position, the less precisely you know its momentum, and vice versa. Another pair of related variables are time and energy. The more accurately you know the amount of time during which an event occurred, the less you know about the energy associated with that event, and vice versa. In theory, a perfect vacuum is a state in which all field values are constantly equal to zero. But the Heisenberg uncertainty principle says that if we know exactly the value of a field, then the rate of its change is completely random. So it cannot equal zero at all times. This means that the mathematical description of unchanging emptiness is incompatible with quantum mechanics. Put simply, emptiness is unstable, so pure emptiness doesn't exist. The idea that a universe containing hundreds of billions of galaxies could emerge from the void is unbelievable. Any mass is a frozen form of energy, and Einstein linked them into a single whole with the famous formula E equals mc squared. However, the vast amount of positive energy locked up in stars and galaxies must be cancelled out by the same amount of negative energy of the gravitational pull between them. In a closed universe, or such that has a finite lifetime and will eventually contract again, positive and negative energies must balance each other out. And this means that the total energy of such a universe is zero. Stephen Hawking wondered how the entire universe can be created from nothing if its total energy must always remain zero, and it's necessary to expend energy to create a body. This is why there must be gravity, and since it attracts, it has negative energy. To separate a gravitationally bound system such as the Earth and the Moon, some work must be done. This negative energy can be cancelled out by the positive energy needed to create matter. But it's not that simple. The negative gravitational energy of the Earth, for example, is less than the positive energy of the billions of particles that make it up. A body like a star will have more negative gravitational energy, and the smaller it is, the greater its negative gravitational energy will be. And before the negative gravitational energy can become greater than the positive energy of matter, a star will collapse or shrink into a black hole, and a black hole will have positive energy. That's why empty space is stable. Bodies such as stars or black holes cannot simply appear out of thin air, but the whole universe can. Quantum mechanics also agrees with the conclusions made by Stephen Hawking. American scientist Alexander Vilenkin showed that a tiny piece of vacuum filled with energy can spontaneously appear from the initial state of emptiness. Under the influence of the negative pressure of cosmic inflation, this piece of energetic vacuum will start to expand. In a couple of microseconds, it will reach cosmic dimensions, emitting a stream of light and matter, eventually creating a Big Bang. So there it is, an ingenious explanation. The universe came from nothing. There was nothing before, no energy, no space, no time. But this nothingness was sustainable. And it makes no sense to ask the question of how long this nothing existed, because in the era of nothing, there was no such thing as time. The world arose as a result of a random quantum fluctuation of the void. So, is the most global question solved?
No.
And is it the most global one after all?
Because if there's no time then why does time matter now?
Maybe a more significant question would be if this quantum fluctuation was random. Einstein once said, God doesn't play dice. So what does all this mean? And what prevents a tiny piece of a vacuum filled with energy from reappearing so that a new Big Bang occurs and destroys humanity with a 100% probability? There are fundamental constants in the world of physics. With their help only, you can derive all physical laws. These constants include the speed of light, the gravitational constant, Planck's constant, the masses of the electron and proton, and the charge of the electron. Physicists noticed that if any of these constants differed even slightly from their value, our universe wouldn't have come into existence, and it wouldn't have been enough to change the speed of light from 299,792,458 meters per second to 290 million meters per second. The speed of light is included in the formulas that determine the interaction of protons and neutrons in the nucleus of an atom and the rotations of electrons around the nucleus. So the slightest change in the speed of light would lead to the destabilization of nuclei, their destruction, or at best, a sharp change in their chemical properties. Also, this would dramatically speed up or slow down the rate of fusion inside the Sun. This is because the fusion of nuclei occurs under strictly defined parameters. Their change can lead to either an exponential acceleration of fusion and an explosion of a star, or an avalanche-like fading of fusion, the fading of the Sun and its collapse into a white dwarf. Here's another example. A free neutron is heavier than a proton plus electron system, and that's why the hydrogen atom is stable. If the neutron was at least 0.1% lighter, the hydrogen atom would quickly turn into a neutron. If the mass of an electron exceeds the difference between the masses of a neutron and a proton, then the chemical composition of the universe would change radically. It would lack hydrogen, meaning it would lack stars in their usual sense, and consequently, life. So how were these constants chosen so precisely? This problem is called the fine-tuning of the universe. But there's yet another question. Why is our universe three-dimensional? After all, the Minkowski space, or a geometric interpretation of the space-time of the special theory of relativity, has 4 dimensions, 3 spatial and 1 temporal. But in our universe, there are only 3 dimensions. This is because in other dimensions, our world could not exist. Scientist Paul Ehrenfest discovered that the orbits of the planets lose their stability in 4 or more spatial dimensions. In 4-dimensional space, for example, where the gravitational field of the Sun acts on the planets according to the inverse square law, the planets moving along spiral trajectories would rather quickly fall into the Sun and be absorbed by it. So why are the physical global constants and dimensions picked in such a way that it became possible for the existence of our universe? To explain this, scientists proposed probably the most important scientific principle called the Anthropic principle of physical cosmology. It says that we see the universe the way it is because only in such a universe an observer could arise. Scientists suggested that a person can not only change the universe, but also influence the laws that this universe obeys.
And that's the thing. That's telling yourself that we are truly one of one. Like, you know the odds of that? I don't, but they gotta be astronomical odds for us to be one of one.
Only change the universe, but also influence the laws that this universe obeys. This is why the principle is called anthropic. There are strong and weak anthropic principles. The weak one says that we are obviously not observing an arbitrary region of the universe, but the one whose special structure made it suitable for the emergence and development of life. The strong anthropic principle suggests that the universe must have the properties that allow intelligent life to develop. A variant of the latter principle is the participatory anthropic principle. According to it, no phenomenon can exist until it's observed. Observers may be necessary to give our universe meaning. But there are other ideas in the scientific community. The discussion of the theory of cosmological natural selection, or fecund universes, continues. According to it, on the other side of each black hole located in our universe, a new universe arises. And the fundamental physical constants there may differ from those in the universe containing this black hole. Intelligent observers can appear in such universes where the values of the fundamental constants favor the emergence of life. The process is reminiscent of mutation and selection in the course of biological evolution. Some scientists believe this model is a better way to describe the fine-tuning of the universe. According to the theory of fecund universes, life arises as a result of natural selection. So universes with the right parameters for the emergence of a greater number of black holes would have more descendants, and the same parameters would also favor the possibility of life there. What are your thoughts on the origin of our universe? Let us know in the comments, and don't forget to subscribe to our channel.
Amazing video. I feel like I'm still there and need more. That's why I warned y'all at the beginning that leads you down a rabbit hole, because you want more information about it, bro. And it's just, I don't know, man. It's just hard to grasp on to the reality, or to the belief that, you know, the universe was created from nothing. From nothing. It's in this vacuum, nothing. Then something maybe appeared, and then boom. And then everything aligned just right for us. Now, I'm not complaining. I'm happy I'm here and I'm enjoying my life. You know what I mean? But it's just like a kid who grows up and then goes out and looks for his parents. You know what I mean? That might have left him or something like that, or whatever the case was. Eventually, you want answers to certain questions. And that's all it is. You know, our past. How did we come to be? Those are just intriguing things that some of us have questions about. You know what I mean? So y'all get at me in the comment section and let me know what you thought about this video. Fascinating information. Till next one, I'm gone. Peace.